Before we get too far here, I just wanted to put in the degree measures again. 25 and then 315. Okay, so those are the degree measures. I want to talk about the coordinates again because that's a really important part of this. And so I'm going to just zoom into the first quadrant here first, just to see what we can do here. I know that we've done this already one time, but I just want to do it again because I think it's important that we see it again. So what I'm going to do is I'm going to just focus on this 30-degree triangle right here. And I remember that it was blue, so I'm going to do it in blue. So we have this 30, 60, 90. And this is the 90-degree angle. This is the 60-degree angle. So this is the 30-degree angle, which is why we're calling it a 30-degree angle, right? Because we're looking from the initial side to the terminal side, which is that angle there. Okay, so if we have this and we know that the radius here is 1, we can solve for this coordinate right here on this dot right here by finding the sine and the cosine of the graph. Okay, so let's see. Sine of 30 degrees was equal to, I'm going to call this y over 1. And I'm calling it 1 because that's the radius of this circle. Okay, so y over 1. So that really means that sine of 30 equals y. Well, sine of 30 degrees we found was 1/2. So the y value here is y equals 1/2. So I'm going to put 1/2 here. Okay, so if we call this side 1/2, then we ought to be able to use the Pythagorean theorem using 1/2 and 1 to get this other side down here. So let's do that. I'm going to just redraw that triangle over here for our reference. Here it is. We have a 30, 60, 90. We're looking at that angle. We have 1/2 is here. We have 1 is here. We need to find this value, which I'll call x here because it's going to be an x coordinate right there. All right, so our Pythagorean theorem says that x squared plus 1/2 squared equals 1 squared. All right, so if we do this, we get, okay, 1/2 squared is 1/4 equals 1, because 1 squared is 1 plus x squared, okay? So then we're going to subtract 1/4 minus 1/4. We get x squared equals 3/4. We're going to take the square root of both sides, which is x equals the square root of 3 over 4. And if we go back to radicals, I know this would be the square root of 3 over the square root of 4. And the square root of 4 is 2, so we write the square root of 3 over 2. So we're going to put a 3/2 square root of 3 over 2 right there. So that is the cosine, by the way, of 30 degrees. So what I want to show you here is that really what we're creating here is a point on the graph that gives me cosine of theta, comma, sine of theta. We could do this again for that 45, 45, 90, which is this triangle here. And we could do it again here also. I don't remember what the colors were, but I'm not really going to be too picky. I'll just fill these in for now because now we're going to take that and reflect those across the lines here. So this was square root 2 over 2. This was square root 2 over 2, which is interesting. The cosine and sine of 45 degrees are both the same. This is 1/2 and this is square root 3 over 2. Notice that this is really just the same. I'm just going to do it in green, sorry. 1/2 square root 3 over 2. This and this are similar, and it makes sense, right? We're now looking at a 60-degree angle rather than a 30-degree angle. Okay. For these other spots on the graph, I just know if I have a radius of 1, this has got to be the point 1, 0. This has got to be the point 0, 1. This has got to be the point -1, 0. And this down here needs to be the point 0, -1. So we can fill those in. And now we just have to take all of these values right here, this one, and this one, and reflect them this way, and then somehow we have to get down here also. Okay, so if we reflect across this line right here, the y values and x values are going to stay the same. It's just that the x values are going to become negative because we're flipping across here and we're going the same distance from here to here-ish to get to this spot right here. So my x value is going to be negative 1/2, but my y value is still going to be positive 3/2. Over here, my x value is negative square root 2 over 2, and my y value is positive square root 2 over 2. My x value over here is negative square root 3 over 2, and then my y value is 1/2. If we move that down across this line now, we're going to make the y values negative also, because now we're down below the x-axis. The x-axis is along this line over here. So we're going to flip upside down. Everything in sight is going to be negative. So this is going to still be negative square root 3 over 2. This is going to be negative 1/2. This is going to be negative square root 2 over 2. This is going to be negative square root 2 over 2. This is going to be negative 1/2. This is going to be negative square root 3 over 2. I know I'm going fast through this, but ultimately, you can look this up. So it's not a big deal if you're like, what is happening? This now, what I'm going to do is I'm going to take these three and I'm going to reflect them across the x-axis now, which means just the y values become negative. The x values stay the same. So this is going to be 1/2 negative square root 3 over 2. This is going to be square root 2 over 2 negative square root 2 over 2. This is going to be 1/2. I'm sorry, nope, it's not. It's square root 3 over 2. And then negative 1/2. All right, so that was fun. But the whole reason that I brought this slide here is because we talked about how on the last slide, hopefully you saw in the GIF, that the circumference of the circle is 2 pi radians. So if you start here and you go 1 radian, 2 radians, 3 radians, and then pi radians we got here. So we're going to call this angle pi radians. If we do that whole process again, we're going to go another radian, another radian, another radian, and then another little bit. And so this one is called 0 radians or 2 pi radians. Radians are angle measures, just like 360 degrees means a whole circle. 2 pi radians means a whole circle. So it's just another type of unit. But the reason that we're using that is because it becomes easier to do some calculations when you are using pi's instead of degrees. So I'm going to think about this as a logical thing because I want to split this up in a way that makes sense for me. So I'm going to take this diagram and move it to the next slide so that you can kind of see a cleaner version in a minute. Okay, so here's where we're at. We have done the coordinates. We've started talking about how this is a pi radians angle from here to here. Here I am marking the page up too much again. This is 2 pi or 0, so I'm going to say 0 or 2 pi. The one thing I missed here is this should say 360 also. Okay. We said, okay, if we take this pi angle, this one, and we split it in half, now we're up here. Now this would be pi split in half, or pi over 2. If we cut that in half, now we are at this spot, which is 45. So this is pi over 4. So now, just like we counted by 45s around the circle this way, I'm going to count by pi over 4s this time. So we've done pi over 4, then pi over 2. Now if we go another pi over 4, then we're at 3 pi over 4, and then pi. Okay, go another pi over 4, we get 5 pi over 4. Another pi would be 6 pi over 4, but then let's reduce that fraction. So 6 pi over 4 goes to 3 pi over 2. Another pi over 4 would be 7 pi over 4. And then another pi would be 8 pi over 4. And so now we're back to 2 pi. So that's good. Then let's look at these ones. So what we did was we had 90 degrees and we split it in 3 to get to 30 degrees. So this spot right here must be a pi over 6 because I took this pi over 2 and divided it by 3, pi over 6. So now I'm counting by pi over 6. So I get 2 pi over 6. 2 pi over 6 reduces to pi over 3. If we count another pi over 6, we get back here. If we do another pi over 6, we're back here. And so now this would give me 4 pi over 3. Another pi over 6 gets me here, and that would give me 5 pi over 6. And then another pi over 6 would give me pi. This would be 7 pi over 6. This would be 8 pi over 6. 8 pi over 6 is 4 pi over 3. Then another pi over 6 would get me back to 3 pi over 2. So this one was 8 pi over 3 right here. This one would be 9 pi over 3. This one would be 10 pi over 3. 10 pi over 6, excuse me. 10 pi over 6 reduces to 5. No, it doesn't. 5 pi over 3. There we go. These fourth quadrant ones are a little bit tricky. Go one more pi over 6 and we get 11 pi over 6. And if you check your work, you're back to 2 pi with another pi over 6. Okay, so what you really need to know is that these special angles, 30, 45, 60, they all have radian measures that are equivalent, and they all have pi's in them, and they all have different denominators. Mr. Wiggins does this, and this is maybe a little bit helpful for you to just kind of memorize this a different way. If we look at this one, and this one, and this one, these all end in 6, so they're all sixths angles, okay? These are all these triangles, this one, and this one, and then this one, whoa, and this one, and then this one. I don't know if this is helpful, but these all end in a 3, so they all have a denominator that's a 3. And then there's the middle-sized ones, which are here. These are the 45, 45, 90s, and these ones all end in 4. So if you look at these, I know that I'm drawing over my diagram 18 million times again, but what I'm trying to say here is there are some patterns to kind of either memorize or just notice and figure out how to reproduce for yourself. Okay, that's the completed unit circle. So we have 3 things. We have our degree measures, we have our degree measures, we have our radian equivalents, and then we have our coordinates for each point on the unit circle. I know that was a whole lot of stuff that I just went through, but there are a couple of formulas that you can use just in case you got lost in the shuffle with all of that. If you have a measure of an angle in degrees, so we have degrees, but we want radians, you can put your degree measure into that red circle and then multiply by pi, divide by 180, and that'll give you your radians. If you have radians, that's what we are given, and we want degrees, you can put it into the reciprocal fraction. So multiply by 180 and then divide by pi. That'll give you your measure in degrees. This is sort of a description of how I think about all of this, and if we just quickly do a little unit circle here, here it is, a circle, like this. There it is. Okay. I always remember that half a circle is pi radians. Therefore, the whole circle must be 2 pi radians. You can split that half circle into 4 pieces, so you can cut it into 1, 2, 3, 4 pieces. So now I have 4 equal parts. These are my pi over 4s. Okay. I can also pi it. I can cut it up into 6 pieces, and that would give me my pi over 6s. And remember that those pi over 3's just reduce down. So this would be my pi over 6 there. That's kind of how I remember it. And I know that this is not a perfect system, but it just helps me a little bit to know that there are some patterns going on with it. You can always just take these angles and add 180 degrees to them or a pi to them. So that's how I got to this spot being 7 pi over 6, for example. Normally, during normal school, I would have you memorize this or figure out everything about working with these unit circles, but because we're online and the reality is a lot of people are really comfortable with Googling at this point, I'm okay if you would just like Google the unit circle every time you need it at this point. There is one important kind of concept here with this stuff called coterminal angles. And if we think about the prefix co, that means with. And so the word terminal is, remember, this final side of the angle. And so the coterminal angles on this graph are the angles that end at the same place as this angle. So we could go around just this much, or we could go around a whole nother time, or we could go around a whole nother time. And those three angles are all coterminal because they all end at the same spot on the graph. If you're working with degrees, you can just add 360 degrees. So this is a 60-degree angle. And you can just add 60 degrees. So that would be like an example of that would be 360 plus 60, which gives me 420 degrees. Okay. In radians, that go around the circle is again, so this was our pi over 3 angle. If we add 2 pi to that, we get 2 pi plus pi over 3. And that would give me, okay, well, find a common denominator. I get 6 pi over 3 plus pi over 3, which gives me 7 pi over 3. 7 pi over 3 and 420 degrees lead to the same terminal edge of that angle. If you think about this in terms of like skateboard or snowboard tricks, like when you do a 720, that's spinning around 2 whole times. So that's what a coterminal angle is, if you want to think about that in terms of like a skateboarding trick. Okay. Really the upshot is you add either 360 degrees if you're in degrees, or you add 2 pi if you're in radians. You can also subtract them. So that means that we can get negative angles out. So quickly, if we take our 60-degree angle, and we subtract off 360, we get negative 300. And so negative 300 is going the opposite way around the circle. So negative 300 is an option also. And if you do this in radians going the same way around, we would have our pi over 3 minus 2 pi. And we would get our answer as negative 5 pi over 3. It's negative. Okay, so negative 5 pi over 3, 7 pi over 3, pi over 3 are all coterminal angles. I know we've done some of these, but what I want you to do is I want you to start by taking your degree measure, find that degree measure on the unit circle. 45 degrees is there. In radians, that's pi over 4 radians. The sine of pi over 4 is square root 2 over 2. The cosine of 45 is square root 2 over 2 also. The tangent is the one we haven't done. If this is the x value and this is the y value, or other way around, sorry. That's the x value, this is the y value. Then the tangent is this divided by this. Since they're the same with this one, we get 1. I want you to try to do the other conversions and then evaluating the tangents of and cosines and sines of these angles first, and then you can check your work against my answer key, which is going to come up in a second.